Move along. This is David Hahn from the University of Florida. We've worked with DHS and some of my DoD colleagues. We've worked with David in the past couple of years, developing a few techniques and interested in some of his capabilities. So that said, let's...
Thank you, Mike. What's that? Oh, put the timer.
There you go.
Thank you, Mike. Good morning. Thanks for coming out this morning. I see a few of my atomic emission spectroscopy friends in the crowd, but I'm going to talk about something actually quite different today. It's kind of a new technique we've been working on, which... Is it not on? Oh, there we go. It's a new technique that we've been working on, which we're kind of calling differential, laser-induced perturbation spectroscopy, and I'll kind of talk through why we've come up with that name and talk about some of the applications for standoff detection. I'd like to also recognize my colleague Nico Amaneto at the University of Florida Department of Chemistry, who's not here today. So when we talk about laser-based diagnostics for rapid sensing, I think Mike and Aaron just gave a nice lead in. You know, we have some target system that we'd like to probe, in my case optically, and get some information about the native structure of that target. And so what I want to talk about today is generally some laser material interactions in the deep UV, which will kind of motivate the technique that I'm going to introduce, which is what we call differential perturbation spectroscopy, and then some preliminary and quite preliminary studies for explosives and some biologicals. So I think when we talk about remote sensing, the idea is to use an optical probe, and I'm going to focus exclusively on fluorescence and Raman as my optical probe. There are, again, other techniques like terahertz, but the idea is we want to probe some target, ideally at a distance. There are many current issues. You've just heard about some of them, but I think two that come to mind are, you know, when you go out in the real world, there's so many background signals out there to sort through. And then specificity is a big thing. So can we really uniquely get a signal from a complex environment? So I think what's always nice, and the word we talk about a lot is orthogonal sensing. So can I combine Raman and fluorescence, where each has some limitations? So there's always a motivation to add a new spectral dimension. And I think that's what I'd like to do with our perturbation technique, is we can bring in another spectral dimension to extract new information which wasn't previously present. So let me spend a few slides kind of motivating where we're going, which is laser material interactions in the deep UV, and exclusively we're going to work with the 193 nanometer excimer laser. This is a human hair that's been etched with an excimer laser. The photon energy at 193 is 6.3 electron volts, and that's greater than almost all chemical bonds, CH, CC, CO. So what happens is when this photon interacts with material, it's really strongly a photochemical process. There's not a lot of thermal damage, but you're actually cleaving and photochemically breaking bonds. That allows you to do some really neat things like precise etching. Again, here's a hair, but the eye in the procedure of LASIK. So we know that the excimer is somewhat unique down at this wavelength, and it can do some remarkable things when you're above what we think of as the ablation threshold. But what about when you go below the ablation threshold? So now you expose a material to that excimer laser pulse with insufficient energy to actually make a crater. So you're really not removing material. You're just sending in a smaller number of photons. However, no matter how low of a pulse of energy, even if you consider an individual photon, those photons are still very energetic. So while we don't have enough energy to have a bulk removal of tissue, we can actually still break individual bonds. A single photon can break a single bond. And so there's still this strong laser material coupling, and there's still this direct bond breakage. And if you break bonds, even if you don't break enough bonds to drive out bulk material, you actually can perturb the optical properties. And it's this sort of coupling and perturbation that we want to exploit as a diagnostic. So just to sort of quantify some bond breaking in the sub-ablative regime, we've looked at collagen. So this is collagen solutions, which has a number of peptide bonds. And basically, we can probe that with a deep UV probe, very, very low energy, to quantify the number of bonds. And then we can come back and we can perturb that with the slightly higher but still sublative energy pulse at either 193 or 355, and we can sort of quantify that bond breaking. And at 355, you really don't break any bonds, which is not unexpected because of the photon energy. But when you move to 193, you get a steady destruction of bonds. And it's that bond breaking that we want to exploit as an optical diagnostic. So that kind of brings me to the scheme, which again we're calling differential, and I'll show you why the term differential, then laser-induced perturbation, and then throw in your spectroscopy. So the idea is we have a system, and we probe that with a typical optical probe. This could be Raman, this could be Fluorescence. That's the two probes that I'm going to use, and we generate a signal. So this is the current state of technology in Raman and Fluorescence. Then we're going to turn this laser off, and we're going to move into the deep UV and come back with our excimer pulse, sub-ablative, but still we're going to break and cleave permanently some of these bonds. Now when you've done that, you've actually destroyed, you've altered the system a little bit, and I've sort of exaggerated that. So now we just come back with our exact same probe, our Fluorescence or Raman probe, and we take a second spectra, call it S2. Now, from here to here, we've done something, and this is unique. And now if we then subtract those two signals, we have a differential response, which is tied largely to this perturbation step. So that's a whole new sort of spectral dimension, if you will, which is responding to this deep UV perturbation. And so we can extract that thing. What's nice about a differential scheme is that you help get rid of variations in absolute signals. So if I have some backgrounds, if my signals are up and down, since you're actually subtracting the same signal, you help get rid of that. So number one, that's a big improvement. And then this perturbation effect is highly sort of matrix species dependent, so you're really pulling out a new spectral dimension that might have the ability to mitigate some of these background variations. So that's what we want to look at. So first I'm going to show just a few slides as sort of proof of concept with some thin organic films. So a typical configuration is we're going to deposit a thin layer, kind of micron-ish layer of a material. We'll come and do, in all of the data that I'll show for the fluorescence data, we're going to excite at 355. It's triple YAG. So we basically come in, we do collect and backscatter and do classic fluorescence and do a fluorescence measurement, call that the pre-perturbation or the pre-fluorescence measurement. Then we'll turn this laser off. We'll come in with the excimer at very low energies, and I'll show those energies as we go along, and I'm going to perturb that matrix. Then I'm just going to turn the excimer back off, come back on with the tripled YAG, take another fluorescence, subtract the two, and that's my differential signal. So to look at some of the selectivity, if you will, we did a binary mixture of two organics. These are both laser dyes, BBQ and coumarin. They have some different chemical structure. This one has a nitrogen group, but they all have nice fluorescence in this kind of easily excitable at 355, so kind of between 380 and 400 and 500 nanometers, you get this nice bond. So we did a binary mixture and deposited these on quartz, kind of less than a micron thick. We did the 355 excitation, the 193 perturbation. So we're usually about 300 pulses at 3 millijoules per centimeter squared. So it's about 100 microjoules per pulse absolute energy, and spread out so this way below an ablation threshold, which is typically on the order of 50 or so millijoules. So kind of an order of magnitude plus below the ablation threshold, but nonetheless, we're still going to do some bond destruction. So this is the fluorescent response of the mixture of these two dyes. And you can see the peaks. This is largely the peak that corresponds to that strong BBQ peak, and this is the strong peak that corresponds to the coumarin 450. And so there's a pre-perturbation fluorescent spectrum in blue, and it's very much a convolution of those two materials. And then we come in, we do the perturbation, we take a post-perturbation fluorescent spectrum. We don't have a lot of change, but since we're actually using the exact same signal to subtract, we have high sensitivity to small changes, and this is then the difference spectra between the two. And what you notice is that for the BBQ peak, there's actually almost a slight increase, but statistically there's not much change going on here, and then you get a fairly large reduction in this region of the coumarin 450. So you actually have a differential response between those two species. So we can quantify that by just doing a linear combination of the two and back out the perturbation of the coumarin 450 peak and the BBQ peak. And what we see is about a 5-fold change in the perturbation to those two fluorescent bands. So clearly that's a selective perturbation of one chemical structure over the other, and that's kind of the basic concept that we want to exploit, and then move this on to look at some other materials. So government security applications of this procedure, and I put a question mark because this was kind of a new approach and a new application. So we've done a little bit of work sponsored by Mike to kind of see how this shapes up for some explosives. So I'm going to show two optical probes, fluorescence and Raman. The fluorescence is all done at 355, and again, we're subtracting the post or the pre from the post, and then we do a little bit with Raman spectroscopy as the optical probe. But the concept is the same. Record the Raman spectrum, perturb the matrix, record a second Raman spectrum, and then look at the changes. We looked at PETN and TNT, and we just did a little quick work with some ammonium nitrate. Inherently, this technique, just like Raman and fluorescence, is perfectly suitable to standoff techniques, but everything that I did was really on a benchtop. So, we're talking half a meter kind of optical pass rather than multiple meters. So first I'll look at Raman probe of PETN. So this is just Raman spectra of PETN. 632 excitation is what we use for everything. We heard some mention earlier about deep UV excitation. Now I'll talk about that at the end. But this is just classic visible light, and I'm going to focus on this region right here. So basically, the concept is to record, perturb, record again, and look at the changes. And this is about 100 micrograms per centimeter squared on quarts of PETN. And when you look at the perturbation, again, 300 pulses at 100 microjoules per pulse. Then we do the perturbation. We've normalized to the NO2 peak right here. And when you look at these three particular peaks, we had a statistically valid reduction in three primary peaks of about 50%, whereas the other peaks are largely unchanged. So as a diagnostic, that's a useful piece of information. If one were to key in and start looking for a difference in a Raman spectra in these particular regimes, you might start to mitigate background signals, background fluorescence. So that's, I think, as a proof of concept, this looks good. Same thing with TNT. So again, now we're probing about the same 100 micrograms per centimeter squared on quarts of TNT. Same concept. We're generating the Raman spectra at 632. I'm going to kind of focus in on these two peaks here. And so this kind of walks us through. This is the actual flake of TNT that we looked at. We then hit that, we record a Raman spectra, hit it with 300 pulses of the excimer. And there's not a huge change between the two, so that's essentially a largely non-destructive scheme. Then we come back and look at the post-perturbation Raman spectra, and what we see is there's a sort of shift in the ratio. So if one were to ratio this peak to this peak, we saw again about a 50% change in that ratio. So now one could imagine an optimized portable system that's really looking at two Raman bands and doing a quick Raman perturbation Raman ratio. And again, that has promise as a diagnostic, but this is very proof of principle. We did a quick study. Now we're looking, instead of Raman, as a fluorescence probe, so 355 fluorescence of ammonium nitrate. Hit it with a little bit more, 700 pulses, and then look at the perturbation response. So here's just the raw fluorescence pre-perturbation, and then this is the difference spectra pre to post. And you do get a perturbation, you do get a reduction, but it's largely flat. So basically, we're just sort of uniformly destroying things, and as a diagnostics, that's not very useful. But again, we haven't looked at Raman or other tools for ammonium nitrate. We can extend this now to biological threats, and we did a proof of concept with some bacterial spores. Could we see the difference between two common spores, E. coli, a gram-negative, and bacillus, a gram-positive? Again, we're going to use 355 excitation of the fluorescence, and these are just a monolayer of spores on an agar plate directly. So we haven't separated the spores from the agar, and we recognize that agar has fluorescence as well. But we're going to go right onto the plate, do fluorescence pre and post, do a perturbation. We hit it with 1,000 pulses, and again, low energy, and then look for the response. What's interesting is if one looks at the raw fluorescence, just traditional fluorescence of the E. coli and the Bacillus subtilis, those spectra are identical. And that's a convolution of some fluorescence probably from the agar as well as fluorescence from this layer of spores. So you're certainly not going to see any difference here. But if we look at the perturbation spectra, looking at the E. coli and the Bacillus, so this is zero change, there's a difference there. You start to pull out a little peak here that's not here, and more of a peak here that's not here. So, trying to determine a difference between here is pretty much hopeless. Trying to pull out a difference over here, I think there's some potential. So again, it's a proof of concept. It's not definitive at this point. But I think we kind of get the check mark that there's some potential here. We can also extend this to an imaging methodology without much of a problem. The idea here is you come in with a broad fluorescent probe and just do a fluorescent image. So that's about a 1 by 1 centimeter spot of roughly Gaussian fluorescent pulse of just a uniform white target. So you can collect a fluorescent image, then you could come in and perturb that with the excimer and then record a second image and do the difference in subtraction between the two to bring that two-dimensional imaging. And just as a simple proof of principle, this is just some white cardstock. There's the pre-image, there's the post-image. So that's a uniform target, so there's no features to find. So instead of looking for features, we actually take the excimer and we just gently write a pattern on there and then look for the difference. And very nicely we can pull out. So if you actually subtract those two images, we wrote H nu very nicely with the excimer laser with just 15 shots per spot at 100 microjoules per pulse. So again, very sensitive to a very small perturbation. So now one can imagine doing the opposite experiment, having some feature in this that's inherently there, using a uniform excimer pulse, doing the subtraction, and pulling out those features. So there's a path toward imaging, I think, that's very nice. Now I'm going to go slightly off the Homeland Security track to talk a little bit about biosensing and some preliminary results from some recent experiments. We're going to look at optical biopsy. So that's a big target, a big application. Can we use light to detect things like cancer or precancerous lesions? And there's been a lot of work with Raman and with fluorescence to do that. Again, specificity is a big issue. Physicians aren't going to use something that has 95% success rate or false positive that just doesn't add any value. So the idea is to come in here and probe things like lesions, and can we determine if they're cancer or not. The current issues are not unlike the Homeland Security. You have this lack of specificity, large sample-to-sample variance, lots of background signals can be superimposed on these inherent cancerous structures. So the idea is, can our differential perturbation technique apply to this as well? So we did an in vivo study with some mice. These mice were treated with a chemical called DBMA in mineral oil. Basically, you rub it topically on their skin 3 times a week, and then we tracked these mice for about 8 weeks, actually a little more than 10 weeks. This is known to promote cancer on the skin. So the idea is to track this using our differential probe, 355 nanometer fluorescence and perturbation with the excimer, and to see if we can start to see changes between our control mice, which just received mineral oil, and the ones receiving the cancer promoter, and if we can pull out information with our differential technique before we can sort of see it in a traditional fluorescence probe. And at 8 weeks is when you really start to get the precancerous. If they go to full cancer, you don't need an optical probe. You can just look right at the mouse and see. So the idea is that the skin is still looking roughly normal, but underlying pathology is changing. So this is the control mouse, and this is normal skin. And I'm not a pathologist, but this is the treated mouse at 8 weeks. And this pathology is markedly different than this, and this is very much a precancerous pathology. So at the same 8-week point, this is the traditional fluorescence of the control mouse, this group, and the treated group. And you don't really see much of a difference. And again, you'd be hard thought to say, okay, cancer, non-cancer. But if we do the perturbation and then take the difference, we actually see something pretty remarkable. So this is sort of no change, and this is the control group, which just kind of has a roughly uniform, kind of like the ammonium nitrate, no real strong features, but we get this very distinct structure in the treated group. And we did the statistical analysis and showed very clearly that the perturbation probe adds much better discrimination than a traditional fluorescence probe. We could also combine the two and actually get additional discriminating power. So that looks very promising. So kind of to bring me to the summary, I think that this deep UV laser radiation, this 193 nanometer specifically, can perturb the local matrix, even at subablative fluences. So people don't think that you're really doing damage. It's like sunburn, right? You're doing damage even when you're not noticeably ablating material. And so it's this high photon energy that's breaking these bonds. So this perturbation spectroscopy approach is using different spectroscopy to probe a target and exploit that sort of coupling of the perturbation pulse in the matrix. So again, the idea now is to use a differential response, mitigate these large absolute variances, and add this new spectral dimension. And I think it holds some promise, and it's something that we want to continue to pursue. If you go into the future, the fluorescence quantum efficiency of things like TNT, PETN are just they're not, you can't perturb if you don't have a signal to perturb. So it's not going to work as a fluorescence probe for these explosives. But when we move into Raman, and in particular we talked about the UV resonance Raman, we could actually perturb the UV resonance Raman signal and actually hopefully amplify what we're seeing in our differential perturbation. So I think that suitably for a standoff scheme, using maybe just some simple multi-line algorithms, and so we're excited about that. What's also nice, and Mike hinted at it in his talk, is that 193 and 266, at these levels of sort of 100 microjoules per centimeter squared, those are below the maximum permissible exposure limit, so inherently this can be a standoff technique. With that, I'd like to recognize a few of my students that worked on this and thank Mike Shepard from DHS for funding this preliminary study, as well as the University of Florida, and Jane Spicer was our intermediary at Johns Hopkins Applied Physics Lab. So that brings me to an end. Thank you very much.
Well, we do have time for a couple of questions.
Yes.
All of those DLIPS techniques is going to help you if you already have interference-sensitivity. Like if you run two compounds and you have interference into the two compounds, you're not sensitive enough to discriminate them. Or is this technique going to help you?
Wait, I missed it. What's the thing that my compounds have that I missed? You said if they are.
You have two compounds.
Correct.
On your target, and Raman fluorescence, they cannot help you to discriminate them.
Sure.
Or is this technique going to help you? Or is the perturbation going to help you?
Well, again,
May I have your attention? Please disregard any current audio or visual alarm. There is no emergency at this time. Corrective action is being taken to clear the alarms as quickly as possible. Thank you.
That means you gave a bad talk.
yeah.
Su atención, por favor. No presten atención a ninguna alarma audible o visible. En estos momentos no hay ninguna emergencia. Acciones correctivas están siendo implementadas para apagar las alarmas lo más pronto posible. Gracias.
So I think to answer your question, we see this as when you have a fluorescence spectra alone that's either too noisy or just doesn't have that unique signature, we're bringing in an additional signature. And so now you can use fluorescence and the perturbation spectra, and so it's just an additional spectral dimension that we've shown with the animal study that we actually add discriminating power well beyond fluorescence alone. So I think that's the main hope. Yes, Nate.
So I understand you picked 193 because that's where the laser is, but if you could pick any wavelength or multiple ones,
Obviously that's a great question, and so what we want to do, we've actually just brought in our tunable OPO to now start playing with the perturbation space as well as the fluorescence space. And now you look for that combination of perturbation and fluorescence that really, quote, resonates and gives you that additional power that's not there with either one alone. So that's a great question. That's what we're trying to go to next. Okay. Thank you all very much.